Okay, so from the section exercises at the back of Chapter 8, this question was taken. Suppose a random sample of size n equals 64 is selected from a population with mean mu and standard deviation sigma. For each of the following values for mu and sigma, find the value for mu sub x bar and sigma x bar. So we've got part A, where mu is 20, sigma is 2. Part B, mu is 90, sigma is 5. Part C, mu is 150, sigma is 10. And part D, mu is 200 and sigma is 50. You are going to find mu sub x bar and sigma x bar for each of the four. So take a minute and pause the video, find mu sub x bar and sigma sub x bar, and then you can continue it when you are finished. Okay, so for a mu of 20 and a sigma of 2, our mu sub x bar, the mean of our sampling distribution, is always the same as the mean of the population, which is 20. So mu sub x bar is 20. Our standard error, you're going to take the sigma, the population standard deviation, divided by the square root of 64, which is what the sample size was in this problem, and you get 0.25. For part B, the mu sub x bar is the same as the mean of the population, which is 90. Standard error, sigma x bar, is 5, which is sigma, divided by the square root of 64, the square root of the sample size, so 0.625. Part C, the mean of the sampling distribution is mu sub x bar, which is 150, the same as the mean of the population, and sigma x bar, which is the standard error, is found by taking sigma divided by the square root of n, or the square root of 64, 1.25. And the last part, mu equal 200 and sigma equal 50, so mu sub x bar, or the mean of the sampling distribution, is 200, and standard error is 50 divided by the square root of 64, which is 6.25. Notice that each of these standard errors were calculated without the finite correction factor. So as I said, you will need to do finite correction factor on your homework, but not on anything past homework 12. Okay, the mean of the sampling distribution of the mean for a normal population. Theorem 8.1 states that the shape of the sampling distribution when sampling from a normal population is also a normal distribution. So, if the population being sampled is a normal distribution, then the sampling distribution of the mean is also a normal distribution, regardless of the sample size n. So this means that if you're taking your samples from a population that is bell-shaped, that is normal, then your sampling distribution, no matter how big or small n is, little n is, the sampling distribution will also be normal. So when n is 2, you still have a symmetric bell-shaped curve. When n is 10, you have a bell-shaped curve. When n is 20, you have a bell-shaped curve. When n is 30, you have a bell-shaped curve. When n is 100, you still have a bell-shaped curve. While the curve takes on a slightly different appearance, because what's happening with that larger value of n is that you get more data values clustered about the center, because we saw our standard error decreases, which means we're going to have values that are closer to the mean. And because the values are clustered about the center, you get this peak that seems larger or higher than all the others as n gets bigger. But no matter what happens to the peak, the shape is still considered a symmetric bell-shaped curve. It is still normal. Therefore, if it's still normal, you have the ability to do things like use normal CDF and IMV norm when dealing with a sampling distribution, which is a very, very powerful tool. Theorem 8.2 handles the case when you're taking from a population that's not normal. So not a bell-shaped curve. So it could be skewed left or right or just something unknown. And here's where we apply the central limit theorem. For any population, the sampling distribution of the mean approaches a normal distribution as the sample size n becomes large. This is true regardless of the shape of the population being randomly sampled. So in other words, the population can have any shape. So it doesn't even necessarily have to be a shape that's known, as long as the sample size being used to sample from that population is big enough. And if it's big enough, then the sampling distribution of the mean will be a normal distribution. And when things are normal, you can apply normal CDF and IMV norm and all the principles of a normal distribution. So the question is now, how large is large enough? Because our sample size of size 2 may be small, but is a sample of size 10 enough? Is a sample of size 20 enough? The rule is, first let's take a look at some pictures. If we start with different looking populations, only one of which is normal, the others take on different shapes. This one is a uniform distribution. This is looks like a bimodal distribution. This one is a reverse J-shaped distribution. If we take from this population and take samples of size 2, the resulting sampling distribution takes on a shape that appears like the following. So when samples of size 2 are taken from the uniform distribution, the resulting sampling distribution takes on appearance that looks like this triangle. It takes on an appearance that is some kind of symmetrical, almost like a curve. The reverse J shape takes on something that looks like it's skewed right. The normal distribution, when you take samples of size 2, creates a sampling distribution that is also normal, bell-shaped. Now look what happens when we increase our sample size. Notice how each of the sampling distributions, when we increase our sample size to 5, each of our sampling distributions start to get closer and closer to a bell, a symmetric bell. If we make n 30, each of them is a perfect symmetric bell. So the rule is, when n is greater than 30, then our sampling distribution is approximately a normal distribution. So given the progression of distribution shapes, as n gets larger, we can see that the look of all the graphs is normal around 30. So the general rule for applying the central limit theorem is as follows. A sample size of n greater than 30 is considered large enough to apply the central limit theorem, which means that the shape of the sampling distribution of the mean is normal whenever the sample size is greater than 30. Now this applies when you don't know the shape of your when you don't know the shape of your original population, or your original population was not normal to begin with. If your sample size is greater than 30, then you can rest assured that the shape of the sampling distribution will be normal, and that you can apply all the principles of the normal distribution to it. Okay, so using a population mean of 8 and a standard deviation of 2, find the mean and standard error for the values of n, and then identify the shape of the distribution if it's possible. So we have samples of size 4, 16, 25, 49, 100, and 400. For each of these sample sizes, we're going to state the mean of the sampling distribution mu sub x bar, which is simply, by definition, the same as the mean of the population. We're going to find the standard error by applying the formula sigma divided by the square root of n. So we're going to take 2 divided by the square root of each of the values of n. And we'll put that answer right here. And then we're going to take a minute and think about what the shape of the distribution that comes out of samples of size n would be. So if samples of size 4 were taken from the population, what would be the shape of the sampling distribution? If samples of size 6 were taken from the population, what would be the shape of the sampling distribution? Now, for each of these cases, we're going to assume that we don't know the shape of the original distribution. Let's see. Yeah, we're going to assume that the original population from which these samples were taken has an unknown shape. So we don't necessarily know that we're polling from a normal distribution. So for each of these, let's calculate. The mean of the sampling distribution is always going to be 8. The standard error is simply going to be found by taking 2 and dividing by the square root of n. So the first one is found by doing 2 divided by the square root of 4, then 2 divided by the square root of 16, and that is 0.5, 2 divided by the square root of 25, 0.4, and then so forth. So 0.2857 and 0.2 and 0.1. Notice what happens. The sample size grows, the standard error decreases. So this is a strictly decreasing standard error. The shape of the sampling distribution. When n is 4, the samples were taken of size 4. The result of the sampling distribution has a shape that's unknown. Because it's not greater than 30. 4 is not greater than 30, so we really don't know the shape of the sampling distribution that is the result when taking samples of size 4. Same thing with size 16 and same thing with size 25. Only when the size is greater than 30, 49, 100, and 400, do you have shapes that are approximately normal. And if they are approximately normal, then we can apply all the principles of the normal distribution to it, which is eventually the direction that we're headed. We want things to be normal because if we can apply the principles of the normal distribution, we can answer questions regarding probability when dealing with sampling distributions, and that's a very powerful tool. So that is where we're going to go with this, with the next lecture. The next lecture on Chapter 8 is going to be dealing with probability questions when handling sampling distributions. So if you have any questions on this chapter, which is one of the more difficult concepts to understand, please email me, and I'll see you at the next lecture.